Okay, hello. This video will be the first of a couple on DNS. DNS is the domain name system. This is the service that answers DNS queries. This is the service that converts URLs, or more precisely domain names, into IP addresses. And when Facebook went down a couple of weeks ago, the initial assumption was that the cause of it was DNS, because it's always DNS, to quote a popular meme. It's always DNS. Is it DNS? Check to see if it was. If it wasn't, you missed something. Check again. If it was, then yes, it's always DNS. So there's this it's always DNS meme, because errors in DNS configuration can cause strange, subtle bugs that don't have obvious causes, but turn out eventually to be DNS many times. In the case of Facebook, Facebook's outage, it was involved DNS, but it was not entirely DNS. Also involved BGP, about which we'll talk more later on. But so DNS for the time being. So DNS is this protocol that does lookup of IP address for a specific URL. This is an example of a naming problem or a naming task. So it's not obvious that naming should be a significant task in network design. It's something that, just like, you know, in language, we take for granted that things have names and people have names, and names refer to things and to people and so on. And, you know, we use the, you know, once we learn the names of things, we can use those names to refer to those things. But in networking, assigning names to things, to network entities, in a way that works, in a way that allows the network as a whole, or all of the entities within a network, to use that name to refer to the thing that is named with that name, is actually a very challenging task in many situations. And, like, you know, why is this? You know, in order for something to be named with a name, properly speaking, it has to be possible for everybody else to refer to that thing using that name. And so when something has a name, this has to be publicly announced somehow, so that everybody knows to associate that name with that thing. And in enormous networks, there can be many things that need names, because you need to be able to refer to those things in order to work with them. In order to send a message to a given node, you have to be able to say what node you have in mind. In order to send a packet to a particular machine on the internet, there has to be some agreed upon way of referring to that machine, so that I can uniquely say that I want the message to go, the packet to go to this particular node among all the millions of nodes, and not to some other node. So like I, as the sender of the message, have to know the name that I can use to refer to that node, and the nodes along the way have to know what I'm talking about when I use that name, so that they forward it on in the right direction, and the node itself, the destination node that I want the packet to go to, has to know its name, so it knows to receive that message when it gets there and not to ignore it, and other nodes that like overhear the message along the way have to know that their name is not that name, so that they know that they can ignore it. In order to send messages from one place to another, we have to all collectively understand the names of all these places involved in the sending of messages, the sources and the destinations, as well as the hops in between. And there are millions and millions of nodes, and to some degree, it sounds like everybody has to know everybody else's name all the time, because at any given moment somebody might decide to send a message from any particular node to any other particular node, and in order for that message to get delivered, those nodes and all the others that end up being involved, however tangentially, have to know the names of those things involved. So there are millions of nodes that all have to apparently know the names of all the other millions of nodes, and there's not one fixed set of nodes for all time. If there were, everybody could be told everybody else's names and write them down on a big table, and then they would know them. And that would be it. But of course, the internet is not static. There are nodes that come into existence whenever somebody opens up their laptop, whenever somebody reboots their iPhone. Nodes come into existence. Nodes connect to the internet all the time and disappear from the internet all the time. And whenever this happens, so whenever nodes join the network, they have to acquire a name in this sense so that they can participate in this communication with the other nodes. And this happens, millions and millions of times, all day long. So in order to keep everybody up to date with the names of all the other players currently online in the network, there's this enormous amount of communication that has to happen, and how that's going to work is a really significant, non-trivial network protocol problem. So I just want to, I'm just trying to impress upon you that naming the assigning names to the nodes of the internet, and keeping the other nodes up to date with one another's names, is like way more non-trivial than it sounds, at first blush. Okay, so what kinds of names are given to these network entities? So the naming problem that I'm talking about here, there are other sorts of network entities that are assigned names on sort of other levels of the stack. The sorts of things that I'm talking about here that need to have names given to them are are routers and hosts on the internet, routers and computers attached to the internet. And the form that the names assigned to those things take is IP addresses. Okay. Other sorts of entities have other sorts of names. So like email accounts, the names assigned to them are email addresses, for example, and nodes within a BitTorrent network have identifiers assigned to them that specify the role that they play within the community of peer nodes in a BitTorrent network, and so on. There are many other examples, but here I'm talking about the most fundamental, primary sort of naming involved in the internet, which is the assigning of IP addresses to nodes within the network. So the form these names take is IP addresses. So we know what IP addresses are. There are these 32-bit numbers that are specified in this A.B.C.D style format, where A, B, C, and D are each 8-bit numbers, but we typically write them as in decimal. So whatever. That's the structure. That's the format of names that are assigned to internet nodes, and so as I was saying, these names have to be once they're chosen, once they're assigned to nodes, these have to be publicized within the network so that the nodes themselves and other nodes can both consistently use these IP addresses to refer uniquely to the nodes that were assigned those IP addresses. Okay, so paging down a little bit. So I say parenthetically here that I'm using name and address basically synonymously here. So on the one hand, we know that the names that being used here are IP addresses. On the other hand, in normal everyday life, we think of the addresses of servers on the internet as being URLs, as being google.com and lehman.edu and www.lehman.cuny.edu, things like that. So in the web setting, we think of URLs as being like the first-class objects. We think of them as being the primary names that web servers, or more generally just servers on the internet, have. We never in ordinary usage, in ordinary internet behavior as computer users, we don't normally ever encounter IP addresses. In order to go to Facebook's webpage, right? We enter facebook.com in the address bar and hit enter, and IP addresses never come into it. So what's going on? If the true names are IP addresses, how is it that we can ignore them in our everyday usage and just use URLs? And the answer is that there's DNS, which is this process that sits in between our behavior as computer users and the underlying network and the underlying identifiers that the nodes in the network have, and translate between these two languages. So although the true names of the different servers are IP addresses, we enter URLs. What happens invisibly every time we enter a URL is that a DNS query is performed, a lookup is performed, searching DNS records to find the IP address that corresponds to that URL. And this is totally invisible to users in ordinary usage of the internet until something goes wrong. But like typically, this is totally invisible, and most users of the internet, are blissfully unaware of the existence of anything involving IP addresses. Most internet users, have never heard of DNS. But it's DNS that allows them to go on with life unaware of IP addresses. So what actually happens is when you enter a URL in the address bar, when you type in facebook.com in the address bar and hit enter, what do I say? So what the user expects to have happen is that a message is sent to, or a user with a certain level of understanding expects to happen is that a request is sent to the web server through HTTP, and the client, the browser, and the web server are able to communicate by having the client send this request in the appropriate HTTP format, and have that result in the web page being sent back. But well, so as we've talked about before, the HTTP request message has a certain format. When you enter facebook.com, the browser decides that it is going to try to get a web page from facebook.com in order to display it to you, and the way that it does that is by sending a GET message in the HTTP protocol format to the URL that you asked for. And the format looks something like this. I think we've seen at least some, to some degree, I think we've seen the HTTP format. So the first line, the format specifies that there's a keyword which is what action this message is requesting. So this is a GET action, and the path on the server that is being requested here, / means the root directory. So typically what this would default, but like the actual physical file, if there is one on the web server that this would point to, would be the index.html file in that root directory. and then following that is the version of HTTP that the client sending this message is using. So HTTP 1.1.1 is what I have here, and you have a line indicating the host, which means the URL of the web server that this request is being sent to. So facebook.com, and then there are a bunch of other attributes that are optional, but that can be specified in the GET request. So except here, what this is saying is that the client, the web browser, sending this message, I will accept as a response something in the form of HTML text. So this is like telling the web server what kind of thing I'm expecting to receive. If this had been a request for a JPEG, so if it had been slash with the address of some image, for example, on that server, then the accept field might have been filled in with something else, some JPEG binary format, and so there are various other attributes that can be included if optionally, and then here we have the blank line, so the extra character return that demarcates the end of the HTTP message. Okay. So what we expect to happen when we enter facebook.com into the address bar is that the browser decides that it should send a message along these lines to facebook.com. And how does an HTTP message get sent? So HTTP is a protocol on the application layer of the Internet Protocol stack. Protocols on the application layer, their messages are sent embedded within messages sent on the transport layer. The transport layer has two main protocols, TCP and UDP. The one that HTTP uses is TCP. So once the browser has generated this text defining the HTTP message that it wants to send, what's actually sent is a TCP message with this text as its body. Okay. And the TCP message specifies the source of the message and the destination of the message, among other attributes. And between the TCP header and the IP header, jointly, they specify the source and the destination each by two pieces of information, by a port number and an IP address, an Internet Protocol address. A little bit more precisely, so the structure of the thing, the structure of the thing looks like this. So So if this is the message body that I'm sending, and so let me paste that in to make this concrete. So when my browser sends this message, the quotation marks here are just pretend, just for visualization, so would not be in the actual literal message. And neither would be the words message body, right? But so when my web browser sends that message, that HTTP message, it gets sent as the body of whoops. It gets sent as the body of a TCP message. TCP, the TCP protocol specifies that messages sent under that protocol have a certain format. The TCP format says that so any TCP message will have a header that has certain metadata filled in, and then following the header is the actual body of the message that is being sent. The header of the TCP message has this certain fixed size of 20 bytes. It's customary to write it as just kind of for visualization. It's customary to picture it as being 5 lines long, 5 rows long, where each row consists of 4 bytes, which is why I have it written this way. There's a bunch of different fields within these 20 bytes that have different pieces of information, different pieces of metadata describing the message. For right now, I just want to point to 2 parts of it. So the first of the 5 rows, which consists of 2 port numbers. So the source port and then the destination port. Because this is an HTTP message, and because the so this is being sent, it's HTTP, not HTTPS. The default port for an HTTP message is 80. So this field would get filled in with the number 80 by default, meaning it would get filled in with 80 because when I entered the URL, I just typed facebook.com. If I had typed in some other port number, and that would be the syntax, so the URL colon and then the number. If I had done that, then that port number would be shown there in the host field of the HTTP message, and that port number would be plugged in here instead of the default of 80. But since I I didn't type a port number, if I'm behaving as a typical user and simply typing in the URL, then the port number that gets filled in will be the default HTTP port number of 80, that being the default port on which a web server will be listening, unless the system administrator of the web server has specified some other port. And the source port will have been auto-generated, will have been chosen by my computer to be the port number that the TCP software on my computer is now going to be listening for responses to this message. So it will have, it will have chosen some number, whatever it is, and when it sends off this TCP message from my machine to Facebook, and which we can think of as being randomly chosen, arbitrarily chosen. And if Facebook responds, Facebook is going to respond with a message that is directed to this port, and that's one of the things that will allow my computer to recognize like where the message is coming from, the role that the message is playing, will recognize that this message is being sent in response to this earlier request that it made. So in response to as a user entering facebook.com into the address bar and hitting enter, after my browser generated this HTTP GET request, it then, or it/the operating system, embeds the text of this HTTP GET request inside of the body of a TCP message that it creates. And TCP is a protocol on the transport layer of the network protocol stack. And just to follow along, so let me just put here like in our notes, kind of to say that we are running, we as the browser are sending an HTTP message, which is protocol on the application layer. The HTTP message is actually getting sent via a request to the operating system to send a TCP message, which is a protocol on the transport layer, TCP transport control protocol, and the TCP message is in turn going to be sent by, if you like, an even lower level part of the operating system that is implementing IP. The TCP message is going to get embedded within an IP message, which is a protocol living on the network layer. And just to be clear, IP is the name of the protocol, Internet Protocol. IP, the protocol uses addresses to name the nodes involved in IP messages, and the sort of names that the Internet Protocol uses are called IP addresses. So it's common for people to talk about an IP, meaning a certain node's IP address. From context, you have to understand whether IP is referring to, whether the words, the letters IP are being used to refer to an address or to the overall protocol that is being used, which references those addresses. So where were we? So our HTTP message got wrapped inside of a TCP message being sent from some port on our system to port 80 on the destination computer. And what does my computer do with this TCP message? The way this gets sent is by, as I said, calling an even lower level function in the API and the operating system that is implementing IP, which generates an IP message, which encapsulates this TCP message. So this TCP message consisted of this header, this header metadata, and then the English, readable text of the HTTP message, the body. From the point of view of IP, however, this whole thing is one long string of characters, or one long string of bytes, and it's this whole thing, the TCP header and the body jointly together as one piece of data, which is the body of the IP message. And that IP message has a header of its own, which also happens to be 20 bytes in normal situations. And like the TCP header, it's common to print it, in books on screens as being 4 rows long, like this. Although it's in fact, it's just 20 bytes of data. There's no actually hitting enter after each of the first 4 lines. It's just 20 bytes of data. But the first 12 bytes consist of various fields that we'll see later on. For the moment, the ones that are relevant to us are the last 8 of the 20 bytes of the IP header, and the very last 4 contain the destination IP address, and the 4 before that contain my IP address. So what is Facebook's IP address? So, oops. So one way to get this so if you go to a command prompt, there's a command called ping, and you can enter ping and the URL of a server or an IP address, but it also works with URLs. And this is a simple command line tool that basically checks to see if the server is up and responding to messages when you ping it, and shows you what the time it's taking for each round trip. Here, so here each response took about 20 milliseconds. So Facebook is indeed up, unlike a certain day earlier this month, and is responding quickly. But the reason I loaded this up was just to see the IP address, which it shows us here when we run ping. So that is an IP address of Facebook. And oops, and so also plugged in here would be my own IP address. Let's I guess maybe the simplest way of